Hey guys, let me know if you have any questions or anything like that. Yeah, just let me know if you guys have any questions or anything. Yeah, the quiz is really just going to be about the heat equation. So this kind of thing right here. Right, where that's measured in joules, that's measured in grams, this is measured in joules per grams degrees Celsius. This is measured in degrees Celsius. So just showing the units below. But yeah, let me know if you guys need any help or anything, or if you have questions about the homework or anything like that. The odd numbered solutions for the homework are already available on Canvas. So 1, 3, and 5. So 2 and 4 aren't on there, but I can go through 2 or 4 if you guys would like. that next week, but basically it deals with the enthalpy involved in chemical reaction equations. So let me see if I can find an example. Like, here's an example where it'll take me a minute to write it out. So Hess's law can get kind of tricky, and yeah, we'll have the notes on it next week, but basically it deals with the enthalpy in chemical reactions. So we know enthalpy is pretty much just the internal energy of a system. So it's always, whenever we talk about enthalpy for chemical reactions, we're always looking at it in terms of a change. So if the enthalpy is negative, overall, it's more of an exothermic reaction. If it's positive, it's endothermic. And so I don't know if this is on the notes yet. It might be on the notes coming up soon. But like in order for reactants to break apart their bonds and become products, it's an endothermic process to break apart chemical bonds, because they want to stay stable like that with the octet rule. They don't want to have their bonds ripped apart. So they need to absorb more energy in order for their bonds to break. And the process of forming new bonds is exothermic. So when it comes to a chemical reaction, like we have two here, you're given a value for enthalpy. So for this first reaction, which is the synthesis of water, here, let me close the window. It's really loud outside. 1 second. All right, so yeah, the first one here is the synthesis of water. And for that chemical reaction to happen, there's an overall, it's exothermic, so the change in enthalpy is negative 572 kilojoules. And the one down here is the synthesis of hydrogen peroxide, H2O2. And that it's also exothermic because it's negative, and it has a change in enthalpy of negative 188 kilojoules. So with Hess's law, you're trying to get a certain chemical reaction done, which isn't these two. It's this one down here, for example. This is just an example that would be like in the homework next week. So we want to try to get this chemical reaction equation, which is the decomposition of hydrogen peroxide, right? So this is kind of like, I'm not sure if it worked well in period 2 or not, but when I did the elephant toothpaste in the sink, it's like hydrogen peroxide and you add bubbles and stuff, and it's supposed to decompose and start expanding. So this is basically that chemical reaction, the decomposition of hydrogen peroxide into water, liquid water, as well as oxygen gas, which is where a lot of the bubbles come from. So you're trying to get this reaction, some target reaction, by manipulating these ones. So for example, I want H2O2 on the left. There's no H2O2 in the first one, but there is in the second one. However, it's on the wrong side, and it's the wrong amount. There's only 1 mole of H2O2 here as a product, and I need 2 moles of H2O2 as a reactant. So you have to kind of play around with the math. It's some trial and error. And so if it's on the wrong side, like in this case, I want it on the left, but it's on the right, you have to multiply your equation by -1, and it just flips the reactants and products. But whatever you multiply it by affects this enthalpy value. So by doing that, by multiplying by -1, this will now be a positive 188. Although I need 2 moles of H2O2, not 1, so I might as well multiply it by -2. So if I want to get 2 moles of H2O2 as a reactant, I have to really multiply this thing by -2. the negative so it can flip to the other side, and the 2 just because I need 2 of them, not 1. So really this delta H will be negative 188 times negative 2, whatever that is. Excuse me. And then you're basically trying to get this equation down here. For this problem, it depends on the problem, but you're trying to get the target equation by manipulating these ones. So for example, if I needed like maybe a 5 or something up here, that's not going to work in this problem. But if I needed like to multiply this by 5, you'd multiply this value by it too. So whatever you multiply your reaction by, like for the coefficients, like whole numbers or fractions, you multiply your enthalpy by that as well. So these delta H's are going to change in the process. And then once you get it to look like this, then you just add up all the delta H's with however they changed. So another thing to keep in mind though is once you do all these flips with these equations here, if they're on the same side, like right here, we have O2 on the left and we have O2 on the left here. If they're on the same side, they add. So this is really 2O2. However, I'm going to end up flipping this reaction. So if I flip this reaction, then the O2s are on opposite sides and then they subtract. So if I multiply this second one by negative 2, then I'm going to have 2O2 on the right, and there's 1O2 up there on the left. So it's going to subtract because they're on opposite sides. It's going to be like 2 minus 1. So you just get 1O2 down here. So basically, to flip the reactants and products, you multiply it by negative. And if you need a certain coefficient up here, like a 2 or a 3, whatever it is, you multiply it by your delta H. As well as if you need to switch them, you have to multiply the negative by the delta H as well. So basically, your final answer is going to be some sort of total change in enthalpy for that one reaction you're trying to get. So you're trying to get some sort of total change in enthalpy. And so Hess's law basically states that the change in enthalpy for a chemical equation is equal to the sum of the changes in enthalpies for the ones that make it up. Like this equation, hydrogen peroxide, if I wanted to make this, I could do it by just using these two chemical equations. However, I gotta like flip them around and multiply them by certain numbers. So that changes the enthalpy involved. And then that's going to equate to the total enthalpy for this thing. Because I don't know what this total enthalpy is, but at the end of the whole process, that'll be my final answer based on however I change these ones. So yeah, it gets kind of tricky. It might be the trickiest thing since stoichiometry for some people, but some people get it quicker than others. It's just kind of like trial and error. You're just trying to get that target equation by manipulating the other ones. And this one is relatively simple. Sometimes you can have 3-step equations, like 3 equations up here, or even 4. On like our unit test, I'd probably just stick to 2 like this. I'm not going to go too crazy with 3 or anything, just because it can get kind of tricky. But yeah, so Hess's law is basically saying the change in enthalpy for a chemical equation, a chemical reaction, is equal to the sum of the changes in enthalpies for the individual smaller reactions that make it up. Like there's other examples too where, let me see. Because that example is good because it's kind of like an easy example, but conceptually might be kind of random. So it'd probably be better if I find a different example. Yeah, I guess this would be good. So and again, these notes will be next week, but just because you might be interested, I'll put these things down. So we have that thing. We have this thing. CO2. Then we have this one. And this one's a little bit longer. It's 3 steps above. So for example, for this one, and a lot of times, not all the time, but a lot of times Hess's law works where your target reactions are all synthesis, kind of like this. This is the synthesis of methane, synthesis of carbon dioxide, synthesis of water, right? Kind of like the last one, actually. It was 2 synthesis reactions. And so we have enthalpies of formation for methane, enthalpy of formation for carbon dioxide, and the enthalpy of formation of water. So this is basically the enthalpy values, the internal energy, right, that causes methane, carbon dioxide, and water to form in a chemical reaction, respectively. So they have their own enthalpy values, their own internal energy values. And I'm trying to get this, which is that last value, then CO2, which is that value. O2 doesn't have an equation. It just doesn't have a, it's not being created in the synthesis reaction ever because it's just an element. It's just O2, right? It's not like a compound or anything. So basically, if I want to find the change in enthalpy for this thing, if I want to find the change in enthalpy for this thing, kind of like what I was saying before, you have to try to manipulate these to look like that. So I have CH4 on the right, but I need it on the left. So I'm probably going to have to multiply this by a -1. CO2 is on the right there. That's where I want it. So that looks good. H2O is on the right there. That's where I want it. That looks good. So yeah, I'm probably just going to have to flip around the first one. And that might be the only thing I have to do. I'm not sure. But it looks like I might just have to flip the first one by multiplying it by -1. So then once you change these delta H's by multiplying them by coefficients or negatives or anything like that, you add them all together, and that equals the total change in enthalpy for this chemical reaction. So Hess's law conceptually just means the change in enthalpy for any chemical reaction equals the sum of the individual changes in enthalpies for the reactions that build it, that make it up. Because these individual reactions make up this big one right here, because it shows how you synthesize each of those compounds. So yeah, that's like the last mathematical thing in this unit. After that, there's like a little bit more notes, but it's more conceptual. But we'll get into that stuff next week. Yeah, so let me know if you guys have any other questions or anything. So Gibbs free energy is also a conceptual idea that we're not really going to use any math in it. And like maybe an AP class, you probably would. But basically, Gibbs free energy kind of takes all these ideas together and kind of summarizes it on the likelihood that certain chemical processes are going to happen. So it shouldn't really be called Gibbs free energy. It should be called Gibbs available energy, because free is kind of misleading. It makes it sound like it just comes out of nowhere, which it doesn't. So Gibbs free energy, because it's named energy, it's measured in joules, just another form of energy, and it's the letter G. And so basically it looks like this. It takes into account what we've talked about with enthalpy, which we know is internal energy, due to a certain system of either a compound or set of atoms, like any sort of whatever the substance happens to be, right? Enthalpy is the internal energy of that system, due to the motion of the particles, as well as the energy in the chemical bonds as well. And then entropy, we were talking about yesterday, relates to how any closed system automatically tends to increase in disorder or increase in multiple combinations or possibilities of randomness. And so spontaneous processes are processes that have an increase in disorder or entropy. So Gibbs free energy takes all ideas together. So Gibbs free energy is this thing, delta G. This is the enthalpy, right? The enthalpy we've been seeing. This is just temperature. And this is entropy, change in entropy. So it works out because they're all measured in joules, right? This is joules, this is joules. Temperature is Kelvin, but then entropy is joules per Kelvin, right? So dimensionally, you can see how it's all just joules because the kelvins are going to cancel out there, right? So basically, with this whole process here, it helps us determine whether or not certain processes are going to be spontaneous, right? So let's see what happens. If I want, we know that spontaneous processes are ones where entropy increases, where more disorder and randomness increases. So if my change in entropy is positive, that's more spontaneous, that's more likely to happen, right? But if this is getting bigger, if delta S is getting bigger, there's a negative in front of it, right? So I want it to correspond with the Gibbs, basically. So if you have something like this, let me just double check something real quick, because I want to make sure I got the sign right there, but it should be. One moment. Yeah, so basically, we know that spontaneous entropy is increasing, it's getting bigger, right? So it's more positive. And so if it's more positive here, if this is a bigger number, then, since this is a difference, this is a subtraction problem here. If this is getting bigger and bigger in comparison with this, it'll be something negative. But if delta H is already negative, which is exothermic, releasing energy to the surroundings, it's just going to become a bigger negative number, which means Gibbs is also going to be just a negative number. So this would be spontaneous. It doesn't look like the word spontaneous, but spontaneous processes would have, all of them have that kind of sign of entropy increasing, enthalpy being released, so negative enthalpy, so exothermic reactions, right? So that's exothermic. And then the opposite would be the case for non-spontaneous. Here, let me. Right, so the way I think about it is, we know that spontaneous things happen when there's an increase in entropy, an increase in delta S. So randomness is going up, right? It's increasing. And so if delta S is getting bigger, if the entropy is increasing, then this is going to be some sort of negative problem, because this is going to be a lot bigger than enthalpy. However, if it's already negative, if it's exothermic, if enthalpy is being released, internal energy is being released from the system, then it's just a really big negative number, which corresponds to Gibbs free energy. And so Gibbs free energy is really Gibbs available energy. So it's like it's kind of like, think of Gibbs as like a lot of noise. Kind of think about Gibbs as sort of like a reservoir of available energy, like a hot object, like a fireplace, right? Some sort of reservoir of available energy, like where it's going to be released to the system. So if something's going to be spontaneous and have an increase in entropy, the enthalpy is going to also be exothermic. It's giving up that energy because exothermic processes release energy to the surroundings, which means the surroundings are going to be in more and more possible states, more and more entropic. And so the Gibbs free energy is also going to be negative. It's also going to be exothermic. So non-spontaneous is just the opposite, basically, where entropy is decreasing, so more order. So you're trying to do something to the system. You're trying to add something to the system to make it more orderly. And the enthalpy is going to be increasing, so it's endothermic. And Gibbs is also endothermic. So when it comes to the positive energy, I think of that as, just endothermic. Negative is exothermic. That's really how you want to think about it. Because again, excuse me, I just think about the ice example. If you have ice in this room temperature room right here, we know that its surroundings are warmer. The ice is cooler. So the ice is going to start melting, right? And so basically, if I want it to not do that, if I want it to basically stay at a cold temperature, I have to add work to it, which is not spontaneous. You have to really have outside help like electricity and putting it in a freezer. So it's a decrease in a disorder. It's more orderly. You're trying to keep it in the solid formation where it's all like closely put together. So yeah, Gibbs free energy just really relates to the available energy of a system and how it can do and how it can use that to do work even. Oh yeah, that should be spontaneous, not Spartans. It's spons with like a period because I couldn't fit it there. Yeah, Gibbs free energy is basically just related to possible available energy that can be used from a system. Oh yeah, good question there. So basically, Kayla, so if you're trying to go from liquid to solid, there's three different, for all these phase change equations, there's like three different ones you got to use. So here, I'll just make up a random number, or I guess we can look at the one in the homework. Let's do that. Let's do the one in the homework. So double check. Yeah, this one's from liquid to solid. So there's one where it's going from 66 degrees Celsius to -3 degrees Celsius. This is like number 5 in the homework. So it's water. So we know water is a liquid from 0 to 100, right? So it's going from liquid to solid here because this is less than 0, right? So you have 3 different equations you got to use. I won't put all the values in like the M's and the C's, but I'll show you what I mean. So you start off with that highest temperature it's at, which is 66 degrees. So no, you don't have to use 100, just to kind of cut a long story short. You don't have to use 100. But you're going from 66 degrees Celsius to 0 degrees Celsius. And then you have to multiply, you have to also add to it the heat that's being used in that fusion stage, where the graph has a slope of 0, where it's either melting or freezing in that fusion stage. So let me just show you real quick. And this is specific heat for a solid. And then this is going to be from 0 degrees minus -3 degrees, or just plus 3 degrees. All right, so basically, kind of looks like this. I can go through the whole thing like with all the math and stuff too if you'd like. I'm just kind of, I don't have a lot of room on here. I'm just kind of doing it quicker. So I think in the problem, it wanted to go from 66 degrees, which is a liquid, to -3 degrees, which is a solid. So you have 3 different equations here you got to add up. The first one is you have the mass times the specific heat capacity of water as a liquid. This is the one that's like 4.184, the heat capacity as a liquid. And you're starting with that highest temperature, so 66. That's the highest temperature it was at. Minus 0, we have to do 0 here because that's the phase where it starts to freeze at, right? Or the temperature it starts to freeze at, right? So that's basically like our little bridge temperature, so to speak, in between those 2 different heat calculations. But then we also need to do this one right here, the heat due to fusion. So this is the quick one. There's no delta T here. fix the Q. There's no delta T here and no change in temperature. So it's just the heat from the mass of the water. And then this is the latent heat of fusion. This is a constant. I think for water, it's 334, I believe, joules per gram. It's like a constant. And then you have to do one more heat equation for when it's becoming a solid. So that's going to be from 0 degrees minus -3. So basically, your highest temperature is the most final one, the T final and the first one, and your lowest temperature is like the lowest initial one, the Ti at the very last one. And so if you have some sort of phase change going on with the water, and if it's going from liquid to solid, we're going to use 0 degrees as our little like bridge temperature, so to speak. So it's going to be the initial temperature in this one, but 0 degrees is going to be the final temperature in this one. So this is really 0 plus 3, right? Because it's minus negative. And then you just add all of them up together. So that's pretty much it. It's just a little bit of a long process. So on the homework that was on, I think it was Tuesday. Yeah, the homework from Tuesday, this is like number 5. But this is also, yeah, I think this is number 5. I'm thinking of a different. Oh no, I'm sorry. The homework from Tuesday was very different. That was the calorimeter problem. This is the one from today. So you could do either 5 or 6. 6 is the same kind of idea, but you're going from gas to liquid. So for 6 instead, it'd be like 100 degrees here and 100 degrees there. That's basically it. Yeah, number 5. So yeah, it's the same idea for number 6, but for number 6, it'd be 100 there and 100 there. That's basically it. So yeah, it's just kind of time consuming. Yeah, let me know if you guys have any other questions or anything. More Q equation, so you'd have 5 heats altogether to calculate and add. That'd be if you're going from gas all the way to liquid or vice versa. So they can be kind of long, but yeah. We'll just stick with water though, because the temperatures for water are much more easy to remember, just 0 and 100. Yeah, let me know if you guys have any other questions or anything. So yeah, it's kind of tricky. For this period we've had so far since March 13th, um, up until I guess tomorrow, um, anything you did can only help your grade go up. So if you didn't do all the assignments we've had so far, I can't make it count against you. But if you've been doing the assignments, your grade will go up. You'll get those points. So it's kind of weird. And then next week we're gonna start making the work mandatory. So it could, in effect, bring your grade down, I believe, but I'm not. I think we're still kind of trying to figure out how that's going to work because they still don't really want to see the grades go down from below March 13th. Um, unless there's like some obviously good reason, like someone just hasn't done anything at all. So it's kind of weird. There's going to be a meeting tomorrow where we're going to talk about it in the morning and hopefully get more information about it. But yeah, so it seems like starting Monday, it's going to be mandatory work. But we're going to cap off this triad with the end of this week. I think this triad was supposed to go on until the 27th, but it's just going to end on the 20th, Monday. So basically, any work that we've done since March 13th, if you've done the work, it'll help your grade go up. If you didn't do any of the work, like if, for example, because I have some students, surprisingly too, some students I have that like usually always do the work all the time and always stay on top of everything. They haven't done anything at all. And like if they haven't done anything since March 13th, their grade's just going to be exactly what March 13th's grade was. So yeah, but then starting next week, it's supposed to start being mandatory. So technically, like in theory, that could bring your grade down if you don't do assignments, if you like, skip out on assignments. But yeah, it's weird because I think they still don't want us to have it go below where it was March 13th. So it's kind of confusing. They kind of made it sound like if it does, you have to have like a bunch of good reasons why the student's grade should go down or something. So we're still kind of talking about it. I don't officially know yet. Yeah, it's kind of all frustratingly up in the air. And I'm sure for you guys it's even more frustrating because you probably want to know how your grades are going to be affected. But no, they shouldn't count against you. So like any of the work we've been doing, like right now in the grade book, they're not counted yet. So your grade right now is exactly the way it was March 13th. And so basically probably this weekend, I'm going to start making those points count. But if you didn't turn in anything, I'm just going to not have that count towards your total score. So it's going to kind of like, it's not going to give you like free points if you don't do assignments. It's not like you can just not do the work and you'll get free points or anything. It'll just be like, it's not part of your total. So your grade's going to be where it was before, like stagnant, like just staying the same. So the assignments you got this week won't count against me. No, so I mean, it shouldn't bring your grade down. Like if you've done all these assignments, if you've been doing all this work, it's not going to, and like, for example, if you maybe got a low grade on a quiz, like maybe the last test we had, maybe it wasn't, maybe you missed some questions or something like that, it still shouldn't be enough to bring your grade down from below March 13th because you also have all these other assignments that you've been doing, which, you get full credit on for the homework and classwork as long as you just complete it. So it shouldn't go down below March 13th's grade. Yeah, hopefully that makes sense. Yeah, let me know if you guys have any other questions. In AP Bio, probably. I'm not too familiar with the coursework, to be honest. Um, yeah, I'm not too familiar, but I'm sure there probably is. It's probably just more like a lot of memorization, I'm guessing, because in life science classes, it's less math. You're more like dependent on just kind of memorizing a lot of information. So yeah, probably, but I'm not too familiar with the coursework. Oh yeah, well then you'll probably like AP Bio more because there's not really much math in it. I mean, there's some math, but there's like more math in our chemistry class than in AP Bio, basically. Yeah, the physical sciences like chemistry and physics, a lot more math. Yeah, let me know if you guys have any other questions or anything. I might end in a few minutes if you guys don't need any other help at all. Well, it's more based on aquatic life. There's probably a decent amount of earth science involved in it too, like the processes of how certain regions have different types of marine life, probably because of different concentrations of um, other substances within those regions of the water. I don't know a whole lot about marine bio though, but whereas normal bio would focus more on like things like just the building blocks of life itself, more in-depth look at things like protein synthesis, cellular respiration, mitosis, meiosis, all that kind of stuff, as well as where it branches out from there. Marine bio probably briefly goes into some of that stuff too, but with marine, you're probably looking more at how marine life works. So you're less focused on things like if you're looking at any sort of like zoology components within it, the zoology involved would probably just be limited to things that exist within the ocean, so like fish, but also aquatic mammals and stuff like that. Excuse me. Yeah, I'm not too familiar with it though. Well, I mean, I kind of been reading a lot lately. Um, well, other than like grading and doing things for online classes and stuff like that, just been kind of reading, trying to do like home workout type stuff because I can't go to the gym. And then just watching some TV. I've been watching King of the Hill a lot lately, which is pretty funny. And yeah, I have a lot of books. I've been trying to take advantage of the time just to kind of do some more reading because I have like a lot of books on my shelf that I've been meaning to get into for like years. I have one book on my shelf that I got like in high school, and it still looks all nice and like I just like got off the shelf at Barnes and Noble or something because I've hardly opened it. So like there's certain books I have that I've been trying to get into. So it's been kind of doing a lot of that. Last week during spring break, I read a lot. I have a a biography I'm reading right now, and it's probably like I don't know 900 pages or something. And I read like almost half of it, like more than a third of it during the break. I just read a lot of it. Yeah, not too much else. I'd like to get a Switch, but they're just so expensive, except for during these days. But I don't really play too much video games, anyways. I have an Xbox, but like I never play it because I'm not that good at video games. Like like physical ping pong or like a virtual ping pong, like a computer game. Yeah, I was never super good at ping pong, but it is pretty fun though. I like the Atari Pong. That's fun. Yeah, I like some simple old school games like Atari Pong or even Blockout, where you're trying to like get the ball to like hit things above you and stuff. But I have like an old Game Boy Advance game that I got when I was like in eighth grade or something in 2004 called a Kirby and the Amazing Mirror. It's like a Kirby game for the Game Boy Advance. I've been playing that, which is pretty fun. I'm really happy and surprised it still works after like 16 years when I got it in eighth grade. So it's nice playing that. That's fun to play. But I kind of miss some of my other games that I lost. I used to have like the Lord of the Ring games and stuff for Game Boy Advance, which were pretty fun. But I'd like to get a Switch, just they're kind of expensive. My brother got a Switch during this time recently, and he's playing Animal Crossing, which looks like it might be kind of fun, but I don't know if it's really my style. Like, yeah, I have like the Halo Master Chief Collection, which I've been meaning to get into, but I'm not super good at like first person shooters. But yeah, not too much though. Just mostly reading. I've been trying to take advantage of the time to do some reading. So I feel like during the school year, because that's the thing. Like I'm busy during this time, but usually during work when I'm physically there in class, I'm busy all day, and then I have to go home and do grading and stuff like that, and lesson planning. But since it's all virtual now, I use this time during the day to also lesson plan and grade and stuff. So by the time it's like 4 or 5 in the afternoon, I just have to do normal house stuff like chores and stuff and not so much work stuff. So I've been trying to use that time just to kind of read and stuff like that. Do you try to get all your work done during the day, or do you kind of like do it at nighttime? Yeah, I usually I just try to get it over with like as much as possible. That way I can free up like the evening. Like even when I was in school, I would like yeah, that's a good idea, sleeping earlier. Because it's kind of tempting to stay up later since I don't have to get up as early now. So like it's easy to stay up late sometimes. But yeah, even when I was in school, I would try to just like do my work as soon as possible, like as soon as I got it assigned, like as quickly as possible, just so I don't have to worry about doing it later. That way you can have more free time to like do the stuff you really enjoy, which is nice. Yeah, I might probably get going in a minute then if you guys don't have any questions or anything. Nice. Well, best of luck with your math homework then. Hopefully it's not too long and stuff. Hopefully we're all not giving too much work. So yeah, take it easy. Have a good one. See you later, Ryan. Yeah, hopefully we're not giving too much work. I'll see you guys later.